Now case 3, either y1 or y2 is 0 at some point. So let's say some point t star in the interval alpha beta. So it can be either y1 at t0 can be 0 or y2 at t0 can be 0. But I know that there is at least one of these who becomes 0 at t star. So without loss of generality, we'll let the one which is 0 at t star as y1. We'll name that one as y1. So without loss of generality, meaning since either one must have at t star equal to 0, among these two, I will name y1 as the one of which such that at t star it is 0. So I'm not losing any case. I'm not losing any generality. So that is without loss of generality. WLOG. And this phrase is used a lot in a proof. So what we have is the following. We have y1, y2 solutions to y double prime plus pty prime plus qty equals to 0. And we also have Wronskian. T is 0 for all t in alpha beta. And we have y1 at t star is 0. So from there, y1, y2 prime will be equal to y1 prime y2 for all t in this interval. So especially at t star, this is also true at t star, right? Now I know that y1 t star is 0, so this whole thing should be 0. So from there, I have two cases, either this 0 or that 0. Okay, so we have either, then this implies y1 prime t star is 0, let's call that 1, or y2 t star is 0, let's call that 2. So for this, we know that y1 solves y double prime plus pty plus qty equal to 0. Then our grand assumption is y1 t star 0. So I have y1 t star 0 as long as I have this condition too. So y1 prime t star is 0. What does this tell you? It tells me that if I have y double prime pty plus, oh, it is y prime here. Yeah, sorry. Pty prime plus qty equal to 0, y at t star is 0, y prime t star is 0, then I have second order homogeneous IVP. And since we are under assumption that P and Q are continuous on the interval alpha beta, how many solutions do we expect from this IVP? Tell me. Yeah, there should be exactly one solution. Unique solution. There should be unique solution from existence and uniqueness theorem. But then y1 solves DE and y1 satisfies this and that from here. Therefore, y1 must be a unique solution to this IVP. So y1 is a unique solution. But if you see this problem, y constant 0 also solves this IVP, right? Therefore, y1 should be constant 0 function. Again, y1 solves this IVP, and this IVP also has a trivial solution as its solution, because y constant 0 satisfies DE as well as initial conditions. But it cannot have two solutions, it must have a unique solution. So y1 should be constant 0, they have to be the same. So y1 is constant 0. Therefore, I can write y1 as 0 times y2, constant times y2. So proof is done. Case 2, little case 2. Suppose now y2 t star is 0. It also has subcases. So let me call that A. y2 prime t star can be 0, or B, y2 prime t star not 0. Either 0 or not 0, only that cases. Only those two cases. If y2 prime t0 is 0, then y2 solves the DE y double prime plus pty prime plus qty equal to 0, and y2 t star is 0, y2 t star is 0, y prime, y2 prime t star is 0. Then again, y2 is a unique solution to IVP y double prime plus pty prime plus qty 0, y at t0 equal to 0 equal to y prime at t0. Since P and Q are continuous, that must have a unique solution. So y2 is one solution, and y constant 0 is another solution. There cannot be two different solutions, so y2 should be equal to constant 0. Therefore, y2 is 0 times y1, constant times y1. So this case is done. Lastly, we're under the case y2 t star 0, y2 prime t star not 0. And remember, we have y1 t star 0. Okay, so in such case, what we do is we're gonna define a big y1 t as y1 t over y1 prime t star. Why can we do this? Because this is not 0. If this is 0, then we are there again, and it becomes case 1, right? So since we are done with case 1, I can assume that y1 prime at t0 is not 0. Since t star is fixed, y1 is given, so this number is a constant. Remember, this is some constant. This is a constant. Okay, y1 is a function, but this is a constant. So let y1 be that, And likewise y2, so we will let yi be little yi over yi prime. So for y2 t star is not 0, so we can divide, no problem. So let big yi be newly defined function for I equal to 1 and 2. And then consider IVP, second order IVP, y double prime plus PTY prime plus QTY equals to 0, y at T star is 0, y prime at T star is 1. So consider this IVP. Then big Y1, big Y2 solves this Y. Let's check. So big YI are nothing but 1 over some constant times little yi. And little yi are each solutions to the homogeneous equation. So any constant multiple of that is also solution to the homogeneous equation. So we see that for I equal to 1, 2, both yi satisfies the DE. Let's check the initial condition. So y1 at t is, it was y1t over y1 t star, y1 prime t star, right here. So what is y1 at t star? So this is fixed, we don't touch it, it is nothing but constant. When we plug in t star here, we have to plug in t star there. So it is y1 t star over y1 prime t star. But what's y1 at t star? y1 at t star is 0. So this is 0. Let's look at y1 prime t. So since y1t is constant multiple of the function, derivative is constant multiple times the derivative of the function. So y1 prime at t star is, this is constant, we don't touch it. We have to put t star right there. And we see that they are the same, so it is 1. So y1 at t star is 0, so it satisfies this. y1 prime at t star is 1, so it satisfies this. Let's do a similar thing for y2. So for y2, again y2t is y2 little y2t over constant y2 prime t star. So y2 prime t is, again this is constant, so it is 1 over y2 prime t star times the derivative of y2, so that's y2 prime t. Okay, so let's plug in T star. Then we plug in T star there. And y2 T star, y2 T star is 0. So this is 0. And when we plug in T star, constant, we don't touch. That's T star. And we get 1. So y2 T star is 0, satisfies this. y2 prime T star is 1, satisfies this. So both y1 and y2 are solutions to this IVP. But again, since P and Q are continuous, it must have a unique solution. That tells us that big Y1 should be equal to big Y2 everywhere. So that tells us that by uniqueness theorem, big Y1 equal to big Y2. That is, big Y1 is little y1 t over y1 prime t star equal to y2 t over y2 prime t star, i.e. y1 t is y1 prime t star times y2 t over y2 prime t star. And see what we have. This is nothing but constancy. So the proof is done. So we have established the statement of the theorem. So PQ con T, Y1 and Y2 are two solutions. If Wronskian is 0 at some T0, then Y1 is CY2 or Y2 is CY1. If Wronskian is 0, then one of the solution is a constant multiple of the other. If two solutions are like this, then we say they are linearly dependent. So that's number 7. The definition. The functions y1 and y2 are said to be linearly dependent on an interval I if one of the functions is a constant multiple of the other on y1, on I. If y1 and y2 are not linearly dependent, we say y1 and y2 are linearly independent on I. Okay, so that's how we call y1 and y2. So corollary, let pt and qt be conti on the interval, and let y1 and y2 be two solutions of the homogeneous equation on the interval I, homogeneous DE. So y double prime plus pt, y prime plus qt, y equals to 0. Then A, y1 and y2 are linearly independent. Sorry, I'm missing many things there. Wronskian never 0 on I. So this, if y1, y2 linearly independent on I, this means y1 is not constant multiple of y2, nor y2 is a constant multiple of y1. So in theorem 6 we had, if Wronskian at some point t0 is 0, then y1 is cy2 or y2 is cy1, meaning they are linearly dependent. That is, if not linearly dependent, then Wronskian T0 is not 0 for all T0 in the alpha beta, right? So if y1, y2 are linearly independent, meaning this, not linearly dependent, then we must have Wronskian never 0. So that implication is true. Let's look at the reverse implication. Let's look at this. So suppose Wronskian is never 0, Wronskian never 0 on the interval alpha beta. Then we get y1, y2 prime minus y1 prime, y2 never 0 for all t in this interval alpha beta. So if y1 is cy2, if y1 is cy2, then if we plug that in there, we get, so if we plug in this into y1, then y1 prime will be cy2 prime, right? So put this there and put this here, then it will be 0. That will be contradiction to this assumption. Likewise, if y2 equal to cy1, we have a similar situation. Wronskian will be 0. So that is again contradiction to this. Therefore, if Wronskian is never 0, that case should not occur. So y1, y2 cannot be linearly dependent, are not linearly dependent, meaning they are linearly independent. So if Wronskian is never 0, then y1 and y2 are linearly independent. So we have if and only if. So this is if y1 and y2 are linearly independent on I, if and only if Wronskian is never 0 on I. B, y1 and y2 are linearly independent, on I blank y1, y2 forms a fundamental set of solutions of star. Again, star is y double prime pt y prime plus qt y equals to 0. So in the earlier we said this is if and only if, this part. Wronskian never 0 on I. And by definition, if Wronskian is never 0, then we said that y1, y2 are a fundamental set of solutions, right? Therefore, we also have if and only if here as well. So as a summary, if I have homogeneous DE star and y1, y2 are two solutions such that y1 is not cy1 nor y2 is not cy1, then y1, y2 generates every solution of the DE because they become fundamental set of solutions, and its Wronskian will never be 0. So it is never 0. Never 0. Not 0 for all t. It will be never 0. So if I have two solutions, and to see whether it will generate every solution, I will check Wronskian at a point, at one point. At certain point, if it becomes 0, then I know that these are not enough. I have to find more solutions to generate all solutions of DE.